Hey everyone, welcome back to a new episode. So in this episode, we're finally going to get Vulkan fully operational. We're still not going to see anything on screen, it's going to be a little bit longer before that happens, but in the previous video we got the Vulkan instance prepared, and there's the 3 steps that I mentioned. You have to create an instance, you need to get all the physical devices, and then create logical devices of the physical devices you want to use. We're only going to be using one, which kind of simplifies things. So we're going to get all that done in this episode, and then in theory, we could start doing something with Vulkan. We're still going to set up a few more things in the following episodes. So, before we start anything, we need some physical devices. The physical devices are just hardware on your computer. In this case, it's mainly the graphics cards, because we need something that can render. So it's usually going to refer to a graphics card or cards on your system. So, we're going to make a new function, and we're going to call it getPhysicalDevices. So we're just going to add that in here. Alright, void, and we're going to go ahead and call that, we'll call it get physical devices. And I meant to capitalize that. Now, we're only going to be actually storing one physical device, but I'm going to call it get physical devices because it is actually locating all of them, and then it's only storing one of them. And later on, we may actually want to use more than one. So we'll come to that. We'll cross that bridge when we come to it. So, after all this debug here, we're going to go ahead and create the get physical devices, give it its scope. There we go. And we want to call that right after we set up the callback. So, there we go. Alright, now we're going to need a place to actually store it. So, back in the header file, we're going to, remember we have these handles here. We have one for the instance and the callback. That's actually not a handle right there. That's just a constant. I'm going to move that out of there. There we go. Alright, and with the physical device, it's not something that needs to be deleted. It's something that's already there. So we don't actually need to use vdeleter in this case. We're just going to create a vk physical device. So vk physical device. And we'll go ahead and call that physical device. So this is normally how you would handle a lot of the Vulkan instances that we're actually wrapping inside the vdeleter class, so it's good to see this anyway. And then we just give it a vk null handle, because it is a handle to something, but we're giving it a null value to start with. Alright, now we actually need to iterate through those physical devices, so we're going to come right back down to the function we made. Alright, and if you remember before, I mentioned that a lot of the times in Vulkan, you actually have to call an enumerate function twice. The first time to get the number of something, and the second time to actually initialize the array that you create with that size. So, what we're going to do is we're going to go ahead and we're going to create an integer, just a uint 32t, and it's going to be physical device count. So that's going to find out how many physical devices are on the system. Right now we're just going to initialize it to 0. And here's the function we're going to have to call twice. It's vk enumerate physical devices. So that's going to iterate through all devices it can find on the system. You need to pass in the instance, which we've already created. And we're going to pass in a reference to the physical device count so that we can set that to the proper number. And then, of course, null pointer, because we don't actually want to store any of these devices we find. We just want to get the number that exists. Alright, and I'm just going to drop this right here. So if physical device count equals 0, the whole thing fails, because if we don't have any physical devices, there's definitely not a graphics card that we can use to render anything, which would defeat the whole purpose. So we throw a runtime error, and no devices found with Vulkan support. Spelling always matters. Alright, so now that we've got that, we're going to create a vector, and it's going to be of vk physical devices. And these are going to be just the ones that we've located. So found physical devices, and we want to initialize it to the size of physical device count. So now that we have that number, we can create a vector that's exactly the right size that we need, and then we're just going to call vk enumerate physical devices again. And this time, we pass in the instance, we pass in the device count, physical device count. There we go. And then we go ahead and pass in found physical devices dot data. So that's going to go ahead and modify physical devices so it has the proper data that we want. All right. So now that we have a list of all of them, we're going to need to iterate through each one of those and check to make sure that it is a suitable device for our needs. So once we've found the one that we want, we're going to go ahead and store that as the physical device that we're using for our engine. And since we really want to pick the best device possible, I'm going to use another recommendation from Alexander's tutorial. He actually mentioned the creation of a rate device suitability function. And what that's going to do is it's going to check each device and not just look for one that meets our needs, but look for the best one that meets our needs and rank them based upon different criteria. So now we are going to create the rate device suitability function. So before we actually start building it, once these devices are given a rating of some sort, we're going to need a way of actually categorizing them, like a way to store each device. So what Alexander recommended was using a multi-map, which is just, a standard map. It has a key and a value, and values are associated with keys, but the difference here is that the multi-map will keep itself organized. It sorts all of the keys. So once it's all finished, we would actually end up with the one that is rated the highest as the last element of the map. So here we go. We need to go ahead and create that map. So std, and we actually need to include map because we haven't used that yet. So up here at the top, just standard include, and then map. It's part of that group. So now that we have that, we can go ahead and std multimap, and this map is going to be an int. That's going to be its score, and then that's going to be associated with a vk physical device. All right, we'll go ahead and call this ranked devices. There we go. So that'll store everything, and let's go ahead and actually get started on the rate device suitability. So we'll just drop down here, int, that's going to be the score that it returns. Planet Vulkan, rate device suitability. I knew I was going to misspell that. There we go. And it's actually going to need a physical device to reference, so we're going to go ahead and have its argument be a vk physical device. There we are. And of course, because we haven't declared this yet, we need to drag it over into the header file. Just drop it right there. Get rid of that. Add a semicolon, and that should be good to go. Alright, so let's get cracking on this. So with the device suitability, first off we need a score. So int score, and we'll start it at 0. Now we actually need to use a couple of calls to get the details about the device. So there's actually a couple of structures built into the physical device. One is the vk physical device features, and we'll just call it device features. And another one is vk physical device properties, and device properties. There we are. So those are going to store a lot of the information we need about the physical device that we're currently checking. They don't have anything in them yet, so we're actually going to need a call, like usual, to give us that information. So we'll call vk get physical device. Wow, that's really off. Physical device properties. There we go. and we're going to use vk get physical device features. There it is. And both of them need some arguments as usual. We're going to go ahead and pass in, oh, we didn't name this, that's kind of important. We'll call it device to rate. And let me make sure I put that in the header file as well. There we are. Okay, so we need to pass in the device that we're checking. So we just pass in device to rate to both of them. And then, of course, we pass in the instance of the device features and device properties to hold the information. So this is the device properties. So there we go. Device features. Okay. So that should get us all the information that we need. Now that we have that, we can start checking against certain details in those that will let us know how well suited our device is. So this is a big one right here. The majority of what's in this device suitability function is going to be straight out of Alexander's tutorial. As always, I'll put a link to it. It's really good stuff, so I would recommend checking it out. So first off, we're going to handle all the stuff based on the properties. So we're going to check if device properties, device type, and we're going to check if it equals vk physical device type. There it is, discrete GPU. So that's actually checking whether or not the GPU that we're checking at the moment is internal on the CPU or if it's its own separate graphics card. And obviously we want the ones that are separate, the ones that have all their own memory and things that will function a little bit stronger than something that's integrated into a CPU. So that is a pretty important thing. This is the type of device that we really want unless we have no other options. So if you find that one, we're going to give the score a massive increase. So there is no way that something that is not discrete will outrank something that is. Alright, so next up, we want to go ahead and increase the score based upon the device properties, limits, max image dimension 2D. Because that is actually going to affect the maximum texture size that this GPU will be able to handle. And obviously the bigger a texture size it can handle, the better it'll look. So we want to rank it based upon whatever its maximum texture size can be. And now for the features, we do want to make sure that the device features include a geometry shader. If it doesn't have one, it, again, isn't going to serve the purposes we need. So we're going to check if not device features dot geometry shader, and if it doesn't have one, we're just going to return 0 because that's useless to us. And then we're going to return the score. So if it hasn't already returned, return score. There we go. If it hasn't already returned, it will return the score, and it will end up ranking these based upon whatever it decided while rating it. So getting back to here, we actually need to go through and call that on each of the devices. So we're going to create a for loop right here, and we're going to use it to iterate through everything in found physical devices. So just const auto and. So we reference whatever its current device is. There we go. Perfect. So it iterates through all the found physical devices one by one, gets each device, and then we're going to say int score, and that's going to be a score for that particular device, equals rate device suitability, and we just pass in the current device that we're checking. So it'll rate each one, it'll return a score, it'll store it, And then ranked devices, our nice little multi-map that we created, we're just going to call rankeddevices.insert, like so, and std make pair. We're just going to create a new pair of these bits of data, and score, and current device. So now, anytime it's received a score for something, it will make a pair out of it. Its key is the score, its value is the device, and they will all be sorted in that multi-map. So once this completes, we've rated all of our devices, we still need to actually grab the best one. So the way we're going to do that is we're going to go down here and say if ranked devices dot rbegin. And rbegin is actually, it's a weird way of phrasing it, but it's grabbing the last element. It's saying, if you were to type in .begin, it would find the first element. If you type in rbegin, it starts iterating through it from the end. So it's finding the final element or the first element if you're going through backwards. So you type in rbegin first, which would grab the key, and we're checking if it's greater than 0. So in theory, if there's anything worthwhile on your computer, the last element of your ranked devices should have a score greater than 0. If it doesn't, it means that everything on your computer is unable to handle what we need. So as long as it's greater than 0, we're going to go ahead and say physical device, which is that handle that we created over here. We're going to go ahead and say physical device is equal to, and we're going to say ranked devices dot rbegin again. And this time we're going to grab second, which is its value. So if the score is greater than 0 for the highest rated device, it grabs the device and assigns it to physical device. And I'm just going to put in an else here. This isn't 100% necessary, but I would rather be notified if there's nothing working out. So we're going to go ahead and put another error and just say no physical devices meet necessary criteria. Alright, and that is everything we need to get a physical device. So that's pretty much it. I mean, step 2 is finished. We have our physical device now. It meets the needs of what we're doing here. So now it's time to create a logical device. Now what a logical device is, it's really just a way of referencing and sending commands to whatever physical device it was that we stored. So we're going to create another handle for the logical device. So we hop right down to our header file again. And while the physical device did not require any sort of wrapping, the logical device is going to need it. So we just go ahead and make another, not right there, the deleter, and we use vk device. We're just going to call it logical device. And then vk destroy device is its destroy function. There we go. So that is our logical device. And now we need to initialize it, just like everything else. So what we're going to do for that, oh, actually, one thing I forgot to mention. The logical device's placement is kind of important. See how we put the logical device here? It needs to be beneath the instance. The instance has to be declared before the logical device, because the logical device relies on the instance. And since these are all going to be deleted automatically when the system shuts down, C++ will delete things in reverse order to their instantiations. So since we created the instance first, it would be the last thing to be deleted out of these 4 here. So you need to make sure the logical device is beneath the instance so that the logical device is destroyed before the instance is destroyed, or you're going to end up having some problems. Alright, so now that we've gotten that out of the way, we need to create the logical device, and we're going to do that with another function. Right here, let's add another one, and this is going to be void create logical device. There we go. Alright, and as usual, we're going to need to take that, drag it over here, make a nice little spot for it, give it its scope. There we are. And then we're going to go ahead and call that in the init Vulkan right after the physical devices. Create logical device. There it is. Alright, so now we can get started. This is going to be a little bit similar to the way that I set up the instance. We're actually going to work through it in reverse because you're going to keep running into things that need to have been declared previously. So before anything, to actually create the logical device, it's pretty straightforward. We're going to wrap it in an if statement again so that we can call an error if it goes wrong. It's going to be vk create device. Alright, we're going to check if it returns vk success, just like so. And as always, we're going to throw an error if it fails. So runtime error, and we'll just say failed to create logical device. Alright, and so the vk create device, it needs a physical device, it needs a create info, and then it needs allocator, a pointer to an allocator, and a pointer to a device, which is going to be the one that gets created. So physical device is obviously the physical device we need. We're passing in the one that we selected. The create info we don't have yet, and that's going to be one of the things that we go up and create. The allocator, again, like everything else, we're going to use a null pointer. And logical device, we're just passing in the logical device that we declared in the header file. And of course, because we're using vdeleter, we can't just pass in the logical device, we need to call replace, like so. So let's get to that create info. That's kind of important. So it's going to be very similar to the one in the instance. We just call a vk device. I really have issues with capitals. There we go. vk device create info. We're going to call it create info. Alright, just create an empty one. And now we're going to go through, and each thing we're going to set to the proper value. So create info.sType, and that's going to be another type structure. So it's vk structure type device create info. Every single one of these is an absolute mouthful, but that's okay. It's the kind of thing you can look up pretty easily. Alright, and then create info. Pnext is once again going to be a null pointer. Create info flags is going to be 0. Create info dot, oh, here's one of the fun ones. Here we go. So queue create info count. We haven't really gotten to the queues yet, so we'll come back to that. We're going to leave it blank for now. And we'll let it give us an error because then we won't forget that it's there. And right after that we need pq create infos, which again, we can't really do until we have a queue, so we'll get to that in a second. Now, once again, we need the validation layer stuff from the instance, so that I'm just going to grab. I don't feel like retyping all that. So we're just going to grab all this right here, the enable validation layers and else for the enabled layer count and enabled layer names. And we're just going to drop that right in here. It is literally the same thing. Alright, then create info. We have enabled extension count. And that's going to be 0. create info, and of course the enabled extension names is just going to be null pointer since we don't have any. And create info, the last one, we have p enabled features, and that's going to be the device features. Let's actually get to that right now, because that one can be resolved pretty quickly. We don't have any device features currently that we're going to care about. We may later, but as of now it doesn't matter, so we're just going to go ahead and create a VK physical device features. It's the same ones that we already checked in the rate device suitability, but right now we don't actually need to mess with any of them. So we're just going to create a structure for it, call it device features, initialize it to nothing, and now that we have that, we can actually just drop it right in where we ask for the enabled features. We just pass in the reference to the device features, just like that. And so that's taken care of now too. And actually, since we already have a create info structure here, even though it's not completely created, let's drop right down here into the VK create device. We can go ahead and put the create info in there right now, just so we don't forget. So we'll pass in a reference to the create info struct. And technically that should work now too. Alright, now let's get to the queues, because this is where things get a little bit trickier. So what a queue is most Vulkan operations, they involve submitting whatever commands that you're giving to a queue. And then all of those queues are stored in what are called queue families. So each one of those families has multiple queues, and they only handle certain types of commands. So what we actually need to do is we need to figure out which queue families our physical device supports, and which ones meet the needs of the commands that we want to send. And once again, I'm going to borrow a pretty handy little idea from Alexander again. He created a struct to hold the index of whatever family you're using. So we're going to hop over to the header file, and outside of the class, because this is its own struct, we are going to create the queueFamily.indices struct. So struct queueFamily.indices. And it's a pretty simple struct. There's not a lot to it. We just we have an integer, which is graphics family. So we're looking for a queue family, one that contains a number of queues that handle graphics calls. And then we're going to search for that in a minute. But this is just going to store the index of where that is on our physical device. And then we also want a way of notifying the program if that struct already is storing an index. So we're going to create a bool is complete, and it's going to return graphics family. That is not what I meant to do at all. Graphics family, if it's greater than or equal to 0. And we're going to initialize graphics family to -1. So right now there's no way -1 could be an index. Doesn't work like that. If it's been initialized to anything 0 or greater, we now have an actual index to check. So bool is complete will return true. Now that we have that, we can actually create a function to find the queue index, the queue family index that we want. So right underneath create logical device, we're going to make another one. And this one is going to return a queue family index struct. So we're going to say queueFamily.indices, and then find queue families. And since this is looking for queue families on a particular device, we're going to pass in another VK physical device. Alright, so we've got that. We're going to go and make that over in our CPP file. And don't forget, we still haven't filled out these queue information in the create logical device, so that's still not going to compile. So we create this, we give it its scope as always. There we are. And let's go ahead and start filling this out. First off, we actually need an instance of the structure. So we're going to go ahead and say queueFamily.indices. Call it indices. Now we need a count. We're going to do the same thing we did every previous time that I mentioned. We're going to make a call twice, first to get the number of occurrences, and then the second time so that we can pass in a vector of the proper size. So we are going to make another uint32t. This is going to be queueFamily.count, and we initialize it to 0. And the call here is vk get physical device queueFamilyProperties. There it is. And we're passing in the device that's our argument, and then the queueFamilyCount, and null pointer, because this is the first call. Now we make the vector. So std vector, and this is going to be a vector of vk queueFamilyProperties. Call it queueFamilies. And we pass in queueFamilyCount, so we have the proper size of the vector. And then I'm just going to copy and paste this. There we go. Make a second call. And once again, for null pointer, we're going to pass in queueFamilies data to overwrite that. A lot of this ends up being very similar, but that's not a bad thing. It means we're very used to it. So now we have to iterate through every single one of the queueFamilies and make sure that it has what we want it to support. So we're going to make int I equals 0. That's going to track the index that we're at. We'll get to it in a second. Then we're going to iterate through all of the queueFamilies. So just like before, const auto queueFamily. Oh, I know I don't want to actually use the same name there. We said queueFamilies before, so this is just queueFamily. It's a singular queueFamily out of the vector queueFamilies. That's the kind of naming convention that could easily screw us up later on, but luckily it's only going to be in this function call, so we'll just be very cautious. So now we need to double check if it meets all the criteria we need. So we're going to say if queueFamily.queueCount is greater than 0, because we need to actually have and queueFamily.queueFlags and vk queueGraphicsBit. Alright, we want that to be sure that we have something that can actually, access graphics calls. So if that's the case, then we found a suitable queueFamily, everything's great, and so for indices, the queueFamily indices struct that we have up here, we're going to say its graphics family equals I. So we're going to say that index right there, that's the one we want. And then directly beneath that we say if indices dot is complete, then we can break. We don't need to keep looping because we already found one, we're done. And then beneath that, to keep the for loop cycling through the indices, we're going to go ahead and increment I. Yeah, so right now the indices is complete seems a little bit unnecessary. We could just break when we assign it, but it is possible that later on we will have multiple types of queues that we are storing in that structure. So just in case, this is how we've built it. And then down here at the bottom, we can't forget this. For the entire FindQueueFamilies, we want to return the structure when we're done. So we're going to return indices. Alright, so after all that's complete, we should actually have something that can locate the index we need and then return it to a function call. Now that we can actually look up a queueFamily, we're going to use that back here in the logical device section that we hadn't created yet. So what we actually need is we need to call that queueFamily and use that to fill out all of the remaining information. So here's what we're going to do. We're going to go ahead and type in queueFamily indices, and we're going to, once again, make an indices instance, and then we're going to initialize that to FindQueueFamilies. So we're just going to actually call FindQueueFamilies on the selected physical device. And since we have that stored, we can just call it directly. So it's going to take whatever physical device we chose, it's going to find the queueFamilies, it's going to locate one that is the graphics family, and we're just going to assign that directly to indices. So that one is already properly set up. And now that we have that, we can start filling out the structure that we needed and didn't fill out earlier for these two sections of queue information for the create info. We actually need another struct that I didn't tell you about. It's vk device queue create info. So the queue actually needs its own create info that we're going to make here. Just like always, you know, queue create info, and we'll start it with nothing. And, you know, actually now that we have it, why don't we go ahead and drop down here, and we're going to go ahead and fill it out right now just so it's already done. So for queue create info count, we're just going to say 1 because we only have one queue family that we're worried about. You could have more, we're not going to bother. And then we're just going to reference the queue create info for the PQ create infos. So that handles both of those. So now technically the create info is filled out as well. We still need to actually initialize this queue create info. So what we're going to do for that, it's going to be a lot of the same information that we filled out a million times already. So queue create info dot s-type. Once again, it is a bit of a mouthful here. It's going to be vk structure type, no spaces, device queue create info. Alright. Once again, queue create info pnext is going to be a null pointer. Queue create info flags is 0. Queue create info dot queueFamilyIndex. This is the thing that we already located, so we're just going to say indices graphics family. So that's the index that was found when we called FindQueueFamilies, and it's storing everything right here in this indices struct. So we can just get its graphics family, and that's the index that we want for its queue family. Then we have queue create info queue count, which again we're just going to set to 1 because we only have 1 to deal with at the moment. Alright, next up we have queue create info dot pq priorities, and this actually allows you to assign different priority values to how the queues are handled. It can be a number anywhere between 0 and 1. In terms, it's a float, so you can give it, you know, decimal values. And since we only have 1, we really only have to set it to 1 because there's really nothing to prioritize. It's only the one queue at the moment. The problem is it won't just take a value. The PQ priorities is expecting a constant float pointer. So what we're actually just going to do is up here we're going to say constant float queue priority. There we go, priority. We're going to set it to 1.0 f for a float value of 1, and then we're going to pass in a reference to queue priority. Didn't show up. Where is it? Queue priority. I'll type it out. Fine. There we go. So that should handle everything we actually need there. And so now, I believe that's everything. So we're just about done. There's only a couple things left to do. Something we need to consider. Now that we've done all this with the queues, it's pretty clear that if your device, your physical device, doesn't have a queue family that meets the necessary criteria, it kind of defeats its purpose. You know, we need to have queues to send commands. So back when we did that rate device suitability, we're going to need to add another call to it, because if we don't have if we don't have the queues, this doesn't actually work. So what we're going to do is we're going to adjust the score in the same way we did down here with the geometry shader. Like that, if we didn't have a geometry shader, it just says this is useless and goes back. We're going to do the same thing for queueFamilies, and I'm actually going to put it up above this because we don't need to look at the features or the properties if it doesn't have the queues. So we're going to make another call, just like before, queueFamily indices equals FindQueueFamilies, and we just pass in the device to rate. So each device, we're going to check its queueFamilies, and then if indices dot is complete, so we're going to check whether or not all of its queues were filled out, which currently is only one. So we're going to say if it's not complete, if it fails, then return 0. This device is not one that we want. So we'll double check that, and that will prevent us from ending up with a physical device that we can't actually use. And there's one more thing we have to do before we finish, because like I mentioned, the queueFamily and the queues within it are actually used to send commands, and we are going to need to send commands at some point. So we're actually going to need to create a handle to the queue. So back here in the .h file, let's go back down to the handles, and the one that we want this time, it's going to be a VKQ, just like so. VKQ, we'll just call it, I'm going to call it graphics queue for now. Okay, so that's a handle to our queue, and we need to assign it, and that's actually handled in when we're creating the logical device. We can just do that right at the end of it. So down at the bottom in the logical device, where are you? There we go. So we have that VK create device, and if this succeeds, we get our logical device. So after that, we can just call VK get device queue, this one right here. And we just pass in the logical device, because at this point, if it got this far, we assume that it worked, and we successfully made our logical device. Then what else does it call for? We need the queue, we need the family index, we need the queue index, and we need the graphics queue reference. So we pass in the logical device, we pass in indices, graphics family, which we have up at the beginning of the create logical device now. We have, where is it? 0 for the queue index. And then we pass in that reference to graphics queue. And so now that will find our graphics queue and successfully assign it, and now we have a handle to it. So let's rebuild the project real quick. Oh, we can just rebuild from here because I made tester game, if you remember in the last video, I set tester game's build dependency to PV engine, so the whole thing will build as one now. Let's see if it still works. Give it just a second to compile. And things look good. Yep, everything's available. Debug callback was set up successfully. You know, let's go ahead and add a couple more in here just so we can see when things work successfully. So, cout, oh, std cout, wow. And we're just going to say logical device created successfully. So now we have some sort of reference to when things succeed. Do we have them for the physical device again? We're going to see again. So it's the layers, the instance, debug, logical device. Yeah, I'm going to make one for the physical device as well. So just copy this. Where was our physical device? Get physical devices. Oh, I suppose I probably shouldn't have copied the whole thing. We really just needed that cout. So if it assigns a physical device, we're going to go ahead and say physical device, and since it's not really being created, we're going to say physical device found. Alright, so that should give us all the feedback we need. And there's actually one other thing that I should have done before and never did. We've been doing everything in debug mode, and it's building fine. You know, everything's great. Eventually, we're going to want to release this stuff, though, somewhere down the line. And as I was testing things, I tried putting it into release mode, and if it probably won't run. It should crash. Yeah, and see, we get some errors, and the reason is because it's looking for some of the library files and it's not finding them. So you'll notice that if we go to tester game here and we open it up, go to the properties, that where we have the library directories, if I open that, and where is it? We have solution dir debug. That's going to look in the debug folder for some of the libraries it needs. The problem is it doesn't have a debug folder when you're handling things in release mode. So I shouldn't have set this particular one for all configurations. So what we're going to do is at the top, let's change it to just release for the moment. We're going to hop back into the library directories, scroll down to where that solution dir debug is, and we're going to change that to solution dir release, because there's also a release folder. Let's try that. Okay? So now that we've changed that, if we scroll over here and we switch it back to all configurations, oh yes, we do want to save the changes. I should have hit apply. And scroll over and you see different options. That's because the library directories for debug and release are a little bit different. That's the only place where it really matters right now. And let's give this a shot now. Let's try running it in release mode and see if it's a little bit happier. Alright, now notice now everything boots up successfully. And another thing you should notice is it doesn't initialize the layers. It checks if the layers are available, but it doesn't actually mess with the layers because we aren't actually setting up any of the layers for error checking when we're running in release mode. So that's a good sign here. So everything's working properly. I'm going to go ahead and switch it back to debug mode so I don't forget. That's pretty much all there is for this episode. So congratulations, if you got this far, you have Vulkan functioning. Everything's been set up and it is initialized and ready to go. There's still a little bit more to do before we get anything on screen, so that'll be taking place in the next few episodes. The next episode specifically, we're going to be setting up a surface, which is what actually allows you to send commands to it's what allows you to render something to the screen. We won't get anything on it yet, but it's going to set up a place to receive the images that are being sent. So, once again, thanks for watching. If you have any sort of comments or questions about this video, feel free to comment. And if you would like to be updated anytime a new one is released, go ahead and hit subscribe.